Okay. In the Zen Summit 2013, and we give a talk about our project named Intel GTG, and the basic idea is the media pass-through approach. Because we want to run native driver, native graphics driver in VM, so we have to present native driver emulated Intel GPU processor, and with the media pass-through approach, we pass through some critical resources for achieving better performance, and also. We trap and emulate privileged operations like a normal device model. And with the approach above, we achieved good performance and moderated multiplexing capabilities. And okay, the history. And our project is an open source project based on Zen. And it was first published in 2013, and its codename known as Zen GT. Our first implementation was on Haswell, which is the 4th generation processor. And at the first beginning, we can achieve about 18% of performance of native Linux in VM. And also, we provide experimental formal support of Windows VM. And at that time, we can support up to 3 VMs. And also, we are targeting about, rich virtual client usage. And the rich virtual client here is, the Citrix Zen client. And now 2 years has been passed, and from 2013 and 2015, and there are a lot of things are changed. And first, let's talk about the brand name. For now, Intel has announced 3 brand names about graphics virtualization technology. The first one is the very traditional API forwarding approach, and Intel also provide a solution about it, and its brand name is Intel GVTS. And the second one is the approach of direct pass-through, and its brand name is Intel GVTG. And for the third one, full GPU virtualization, and this one is our solution, and its brand name is Intel GVTG, which is our topic today. And okay, so for the advantage and disadvantage of the 3 solutions, I think it should be very apparent. For direct pass-through solution, we can only assign the graphics device into only one single VM. And for API forwarding, because it's emulate and packing all the things in an application API level, so it has no media or GPU support, and the compatibility is not good. And so the project information, and we have an official website which has been shown just now, and now our release mode are changed to the quarterly release model, starting from the quarter to 2014, and we have released 6 releases till now. And the recent release should be the quarter 2 2015. And also for customer engagement, Citrix has released Zen Client 5.5 on January 2015. And GTG support on Haswell is one of the release highlight at that time. And also, GTG gas support has been merged to official Linux kernel on 4.1 on February 2015. And for supported guest OSs, we support both the 32 and 64-bit Windows 7, Windows 8, and also Ubuntu. Papers and presentations. For papers, we write two papers which were accepted by Usenix in 2014 and 2015, and also we do a lot of presentations and talks. In 2013, we give a talk about our project ZenGT on Linux Foundation collaboration, and also we give a talk on QL Forum 2014. Let's talk about some technology update. Now we support the new platform, Broadwell. You know that Broadwell is the fifth generation of processor graphics. From a high-level view, you can see that there are no major changes, and from the microarchitecture partitioning, it looks like similar like Ivy Bridge and Haswell. In the left side, you can see there are so many fixed functions and shared functions, and also there are EUs to run shaders, and there are 3 slides. And in this picture, it's an GT3 stepping, so there are 3 slides. And if you bought a lower end, maybe there are only 1 slide or 2 slides here. And also, okay. So the hardware change brings some new requirements and challenges to our virtualization, full GPU virtualization solution. First of all, Broadwell provide much bigger aperture resources, and for more aperture resources allows better scalability. Now we can support up to 7 VMs at the same time, and also the hardware introduced some new command submission interface named execution list from Broadwell. It's a more self-contained command submission interface with better programmability than the legacy RAM buffer mode on Haswell, and also the memories, the GPU memory subsystem was heavily changed on Broadwell, and we call it the enhanced per process GGTT. You know that Intel graphics processor, it has 2 dedicated graphics memory space. One is global GTT and another is the per process GTT. For global GTT, it can be used for some privileged operations like what kernel does in the kernel space, and for per process GTT, it was used like user space in kernel. And the page table format of GPU of Broadwell was heavily changed. Now the page table format of GPU is just the same as the IA page table, and it supports 3 or 4 levels, and the page table entry, the length of the page table entry has been extended to 64-bit, and also driver usage has also been changed because that on Haswell driver are intended to use an alias PPGDT model, which means that all graphics contexts share only one graphics memory space. And on Broadwell, drivers start to use the so-called here the true per process GTT memory space, which means that each graphics context can share only one, can have its dedicated graphics memory, which means that you can use bigger and much textures and a lot of video surface at the same time. But it also brings us a lot of challenges. The old virtual PPGTT implementation. And in the last talk, we have talked about that because our project doesn't rely on IOMVU, so all the GPU memory page table are shadowed. And for the old PPGTT implementation, it has so many, assumptions. Like, it assumes that all graphics hardware engines are only use one PPGDT page table, and it only support, two-level page table on Haswell, and the code is not, well written to support multiple platforms. Oh, you know that our project start to support two platforms, support both Haswell and Broadwell from the from the newest release. And also the true PPGDT may incur, much more write protection traps because, our we track guest page table via a write protection mechanism, and when the new PPGDT page, when the new true PPGDT mode was used, and there will be a lot of write protection traps. So we have to rewrite the whole Virtual PPGDT implementation, and to meet the new requirement, like multiple platform, and also the new memory subsystem on Broadwell. The major features are we can support 2, 3, 4-level page table in our new Virtual PPGDT framework, and also we can support true per process PPGDT mode by remove all the assumptions in the old implementation, and also we introduce a PV notification channel to guest, so that guest can notify our vGPU device model that it creates a page table, it destroy a page table, so that we can keep all the shadow page table used. We can keep all the guest page table in our page table cache. Oh, here the page table in the page table cache should be the shadow page table. Also, we introduce a reference counting. Because in the KMD driver, guest sometimes it will share page tables among different engines, and sometimes it will share page tables on some graphics memory space, just like kernel space and user space in kernel. So the reference counting mechanism can reduce the time cost of create a shadow page table, and also it can save memory space occupied by the shadow page table. And at last, we introduced a big optimization. We call it out of sync shadow because there are so many traps caught by write protection on Broadwell, and so when the out of sync shadow mode is enabled, when guests try to modify its page table entry, and we will remove the write protection and let guests modify it freely. And then when guest will submission graphics workload to hardware, and we will sync all the modified page table entry at that time. After this big optimization was introduced, the performance of Windows are increased meaningfully. The 3D performance of Windows are increased about 50%, and the 2D performance of Windows VM are increased about 80%. Okay. So new usage scenarios. One team inside Intel, they achieved a POC project on Intel SoC virtual platform. The basic idea is cluster and head unit consolidation. It means that they run cluster and head unit consolidation in only one CPU. And in VM1, they are just run some very basic very basic programs to show the speed meter and also the engine RPMs. And in VM2, they can show maps, GPS, and also playing videos. So they want use GPU virtualization technology to accelerate the program inside VM2 and to provide better user experience. Okay, and so the next new usage scenario is Visual Cloud. In the first usage, video delivery, so much video provider, they build their video transcode farm on cloud inside VMs. So our solution can let them to use the GPU acceleration power to accelerate the transcoding. And also for the cloud graphics, graphics provider, and they provide remote application and also remote rendering, remote gaming on cloud inside VMs, and with our solution, they can provide better user experience. And for visual understanding, that usually that it will use complicated algorithm to recognize meanings from pictures, and also because we support OpenCL and open computing language. Such use case inside VM can also benefit from GPU acceleration. So GPU has become a very basic foundational service in Visual Cloud. And okay. So let's see a case study, Media Cloud. In 2015, Intel and Huawei announced an virtualized media server solution on MWC. And I think the idea should be similar like NFV, because they put network function into a virtual VM, and here they put media server media function into VMs, just like NFVs. And also the media pool can provide so much can provide function of encoding, decoding, and also video composing. With the power of the media server pool, there are some requirements like video on demand and also video conferencing. Such use case can be benefits from the GPU power. And also it's reveals some performance challenges to us, like memory intensive and real-time processing, and the mixed media and 3D usage, which increase GPU utilization overhead a lot. And so we do an analyze, and also we figure out the problems. The Smart Shadow GPU period table here is the out-of-sync shadow period table we mentioned before. It provides about 17% performance gain, and others are cross-engine synchronization, because Intel GPU pipeline is doing bit stream packing in a dedicated pipeline, and for the MC and MV encoding, it's in another pipeline. So after enable the cross-engine synchronization, and we got about 20% performance gain. And also, it's interesting that when the multiple video, when we are using multiple video channel, and maybe the bigger resolution, increased memory system will provide us some performance gain. In this case, it's provide us about 10% performance gain. And okay. So the next topic is GTG Upstream. And for GTG Upstream, it's our main focus on 2015. And this is a basic architecture of the GTG. The core logic of GTG are based on the MTP wrapper driver here, and also it requires some MTP service in the hypervisor with the two components here, and the whole solution, GTG should work. And for required MPT service in them, because the first implementation was based on them, and some of them are already supported and provided by them, and some of them are still in the process of upstream, like on-demand memory write protection, and we have talked about it. We rely on the mechanism to track that guest GPU page table. And I think most of this part has been upstreamed, and only a trivial like arbitrary-based range set are left to discussion. And also there are still another part still under discussion and still not started, like map and unmap guest memories, because we have to scan the GPU workload from guests to prevent that malicious guest want to do something bad. And also we our shared page table are rely on the GPA to HPA translation service. I think this kind of service are under discussion and has been discussed about I can remember that maybe several rounds in the community. And for now, I think its status should be upstream, not started. And for MTP wrapper driver in domain kernel, in domain 0 kernel, it including maybe two parts. And the general MTP framework are the main part of GPU device, virtual GPU device model, and it's totally hypervisor agnostic. And also, there are MTP wrapper driver glue layer. It sits between the MTP framework and the hypervisor specific service, so that it can run both. It can run the MTP framework on both hypervisor, like Zen and QVM. And this part are still upstream, not start. For other components, for Linux guest support in i95 driver, we have our guest support on Haswell has been merged, and for Broadwell we are still in the process of upstream, and because we emulate an GPU processor to guest, there should be a legacy PCI device in QEMU, and this part of components are still in the process of upstream by some colleagues from Fujitsu. And also, there are some trivial modification in the tool stack, like switch, which HVM are enabled for the GTG, which are not some trivial modification like that. We are still not start. Okay. Okay, summary. As you can see that our project are great evoluted from the 2013, and because more and more customers are interested in our project, and there are much more usage model come out, and on 2015 our main focus is going on forward to upstream. So for call for actions, please try and feedback. You can give us comments or feedback on our GitHub repo, or also join our mailing list. You can find it. You can find it in the 0.01.org. And also, please help us to upstream, and welcome to comments, discussions, and all kinds of things to make make effective progress in our upstream process. Okay, thank you.
I have a question about the performance of the GPU. You mentioned the real time in the new use case scenario for the cluster consolidation. So I'm curious what the real time means here. So
the real time, I think it should be the concept of the embedded system. I think it should be the challenges when you using some things in embedded system. For now, I think the real time here. I think should be a
guaranteed service.
Yeah. Embedded system.
So if the real time is the guaranteed performance, what if does the GPU, the Intel GPU, achieve the isolation between the different VMs, like the 7 VMs using the GPU? For example, like these VMs are running some videos and using a lot of memory, and this memory may interfere with each other in the last level cache.
Oh yeah. We have a lot of patent on the QoS to keep to keep that. We have some policies to to maybe this VM can use some resources of GPU. Maybe by percent or by some kind of things like that. Yeah.
So which kind of resource do you consider?
Like the GPU usage, and also the graphics memory, and also the power management. Yeah.
Okay. How about the cache?
How about what?
The cache, the last level cache shared with the CPU.
The last level cache are totally controlled by the hardware. In fact, Intel GPU implementation, the last level cache are some portion of the last level cache are kept used by the GPU only, and for the other last level cache, the other part of last level cache are totally shared, beyond between the GPU and the CPU. Yeah.
I see.
Yeah, but I didn't see any special policy to control the question you mentioned, that you want to maybe prevent GPU put something into last level cache. But in GPU page table you can specific this video surface or this kind of buffer object you want to cache it in which levels, like last level cache, or the in the high end of Intel GPU it has the embedded DRAM. You can specify that you cache this object in that embedded DRAM, not cache. Yeah.
Okay. Thanks.
Yeah. Okay.
Question. So what is the relationship between the PPGTT and an IOMMU? Or did I say that wrong?
Yeah. It's complicated to explain. The PPGTT model is looks like a dedicated graphics memory space for graphics context, and for now I think it doesn't really you can use IOMMU to do the GPA to HPA translation, so that we cannot we don't need to shadow the whole PPGTT page table. We just use IOMMU to do that. But in our design, we use shadow page table approach for PPGTT, so we don't rely on IOMMU. Yeah.
Okay, so you're saying that IOMMU could possibly be used inside of the PPGTT, which is like an address space?
Yeah. There are so many, approach to use IOMMU in our design.
Okay.
Yeah, but we didn't rely on it because some low end of Intel SoC platform they doesn't have IOMMU. Yeah, that will limit our usage model. So we are using shadow GPU page table now. Yeah.
Okay, thank you.
Okay.
Is per processor, GTT able to access all of the system's memory?
Yeah.
So what's the difference between the GTT, no matter it's per processor or global, difference between the GTT and the IOMMU?
For now, the GTT is the here means the graphics memory space, and the GTT is looks like the something like page table. It's just like a 3-level page table, and when guests want to use GPU, like in direct pass-through, it will fill the guest physical address inside the PPGTT or GGTT page table, right? And then you have to enable IOMMU without shadow page table to do the guest physical address to host physical address translation, right? Without IOMMU, you can't do that. But in our solution, we are using shadow page table to do the graphics, the guest's physical address to host physical address translation. So we don't rely on IOMMU. Yeah.
Okay, thank you.
So IOMMU can be a tool to do the translation to simplify our design. Yeah, but we don't rely on IOMMU. Yeah.
Thank you.
Okay, I think that's all. And if you have more detailed question, want to discuss, maybe you can find me to talk. Okay, thank you, everyone.